seeing wonders of innovation.
Part 1. The invisible enemy, friction. Imagine you are sitting inside a train. It starts moving slowly. Then it goes faster. Then even faster. Everything feels smooth. But something is fighting against the train every second. You cannot see it. You cannot touch it. But it is always there. That invisible enemy is called friction. Friction is a force that resists motion. Whenever two surfaces touch, they create friction. When you walk, your shoes press against the ground. When you write, your pen rubs on paper. When a car moves, its tires grip the road. All of this is friction. Now here is the important part. Friction wastes energy. A lot of energy. Scientists estimate that around 20 to 30% of energy in machines is lost because of friction. That means almost 1/3 of energy is not used for movement. It turns into heat instead. Think about that. Huge amounts of fuel and electricity are simply wasted. Now let us focus on trains. Traditional trains run on wheels. Steel wheels roll on steel tracks. This may look smooth, but it still creates friction. At low speeds, this is not a big problem. But as speed increases, friction becomes stronger. The train needs more power to keep moving. More power means more energy. More energy means more cost. And there is another problem. Air resistance. As a train moves forward, it pushes air out of the way. At low speeds, this is easy. But at high speeds, air becomes like a wall. Above 300 kilometers per hour, air resistance becomes the biggest challenge. The train must fight against the air every second. This requires even more energy. Now imagine trying to go faster than that. The faster you go, the harder it becomes. This is why traditional trains have a speed limit. Even with powerful engines, they cannot go too fast. Friction and air resistance stop them. For many years, engineers tried to reduce friction. They made smoother tracks. They improved wheel design. They used better materials. But no matter what they did, one problem remained. The wheels were still touching the track. As long as there is contact, there is friction. So a new idea was born. What if the train never touched the track at all? What if it could float above it? No contact. No friction. This idea sounded impossible at first. But science had a solution. Magnetic levitation. Instead of using wheels, powerful magnets could lift the train into the air. The train would float above the track. This would remove mechanical friction completely. Suddenly, everything changes. Less energy is wasted. This means higher speed and better efficiency. It also means quieter travel and less wear on parts. But removing friction is only half of the story. The next challenge is air itself. To go even faster, we must remove the air too. This leads us to a bold new idea. Vacuum trains. A future where speed has almost no limits. Where travel becomes faster than ever imagined on Earth today.
This part introduces friction as the hidden force, limiting motion and wasting energy. It explains how constant contact in traditional systems creates inefficiency and heat losses. The concept builds awareness that speed is not only about power but also about reducing resistance. It sets the foundation for understanding why eliminating physical contact becomes a revolutionary step in transportation, engineering, and design.
Part 2. Floating without touching. Now imagine something strange. A train that does not touch the track at all. No wheels. No contact. No friction. It sounds like science fiction. But it is real. This technology is called magnetic levitation, or maglev. The idea is simple. Magnets can push and pull without touching. If you place two magnets with the same poles facing each other, they repel. They push away from each other. Scientists use this force to lift trains into the air. The train floats just a few centimeters above the track. This small gap changes everything. There is no contact, so there is almost no friction. This means the train can move more easily. It needs less energy to stay fast. Now let us understand how it works. There are two main types of maglev systems. The first is electromagnetic suspension. In this system, magnets pull the train upward toward the track. Sensors constantly adjust the force to keep the train stable. The second type is electrodynamic suspension. This system uses superconducting magnets. These magnets are very powerful. They create strong magnetic fields that push against the track. This keeps the train floating safely. Superconductors are special materials. When cooled to very low temperatures, they can carry electricity with zero resistance. This makes the magnetic force even stronger and more efficient. Japan has tested this system for many years. Their maglev train has reached speeds of over 600 kilometers per hour. That is faster than most airplanes during takeoff. Now think about what this means. No wheels means no wear and tear. Traditional trains need constant maintenance. Tracks must be repaired. Wheels must be replaced. But maglev trains reduce these problems. This saves time and money. They are also quieter. Since there is no contact, there is less noise from friction. Passengers experience a smooth and silent ride. But there is still one challenge. Even without friction, the train still moves through air. And air creates resistance. At very high speeds, air becomes the biggest problem. It slows the train down. It also creates heat and noise. In fact, at speeds above 500 kilometers per hour, most energy is used just to push air away. So even with maglev technology, there is a limit. Engineers realized something important. To go faster, removing friction is not enough. They must also deal with air resistance. This leads to a powerful idea. If air is the problem, remove the air. Create a space with very little air inside. A vacuum. Inside a vacuum, there is almost no resistance. Objects can move much faster with less energy. This idea is now being tested in new systems. One of the most famous concepts is the Hyperloop. It uses maglev technology inside low-pressure tubes. This combination could allow trains to reach speeds over 1,000 kilometers per hour. That is close to the speed of sound. But building such a system is not easy. It requires advanced engineering and careful design. Still, the potential is huge. Faster travel. Lower energy use. A new future of transportation. The journey from wheels to floating trains is only the beginning.
This section explains magnetic levitation as a solution to mechanical friction. By using magnetic forces instead of physical contact, motion becomes smoother and more efficient. It introduces superconductors and advanced systems that allow heavy trains to float. The core idea is that removing contact changes the limits of motion, opening the door to faster, quieter, and more energy-efficient transportation systems in the future.
Clapperboard Part 3, The Wall of Air. Now imagine you are riding a bicycle. At slow speed, it feels easy. But as you go faster, something starts pushing against you. That force is air resistance. Air may feel light, but at high speeds, it acts like a wall. The faster you move, the stronger it pushes back. This is a major problem for fast trains. Even maglev trains, which have almost no friction, still face air resistance. At speeds above 300 kilometers per hour, air becomes the biggest obstacle. In fact, engineers say that at very high speeds, more than 80% of energy is used just to fight air. Think about that. Most of the energy is not used to move forward. It is used just to push air out of the way. This is not efficient. It limits how fast trains can go. It also increases energy cost. Now let us understand why this happens. Air resistance depends on speed. When speed doubles, air resistance increases much more than double. This is because of a rule in physics. Air resistance increases with the square of speed. So if you go twice as fast, the resistance becomes 4 times stronger. If you go 3 times faster, it becomes 9 times stronger. This makes high-speed travel very difficult. Engineers try to solve this problem in many ways. They design trains with smooth shapes. They make pointed noses to cut through air. They reduce gaps and rough surfaces. All of this helps. But it is not enough. At very high speeds, air still wins. Now imagine a different idea. What if there was almost no air at all? No air means no resistance. This is called a vacuum. In space, there is almost no air. That is why spacecraft can travel at very high speeds. Engineers want to create a similar environment on Earth. They design long tubes. Inside these tubes, most of the air is removed. The pressure is very low. This creates a near vacuum. Now place a maglev train inside this tube. The train floats using magnets, and it moves through almost empty space. This combination removes 2 major problems. No friction. Almost no air resistance. Now the train can move much faster. Some designs suggest speeds of 1,000 kilometers per hour or more. That is faster than most commercial airplanes. Travel time between cities could be reduced dramatically. For example, a trip that takes 5 hours today could take less than 1 hour. But creating a vacuum is not simple. The tube must be strong and airtight. Pumps must remove air continuously. Any leak can reduce efficiency. Safety is also very important. The system must protect passengers at all times. Even small errors can cause big problems. Despite these challenges, research is moving forward. Countries and companies are investing in this technology. They see it as the future of transportation. A future where distance becomes less important. Where cities feel closer together. The idea is bold. But history shows that bold ideas can change the world. From steam engines to airplanes, every breakthrough once seemed impossible. Now, the same is happening again. The wall of air is strong. But with science and engineering, we are learning how to break through it.
This part highlights air resistance as the next major barrier after friction. It explains how resistance increases rapidly with speed, becoming the dominating limiting force. This concept shows that even advanced systems cannot escape physics. It introduces the idea that to achieve extreme speeds, engineers must rethink the environment itself by reducing or removing air from the path.
Clapperboard Part 4, Creating a World Without Air. Now let us go deeper into the idea of a vacuum. A vacuum is a space with very little air. It is not completely empty, but the air pressure is extremely low. On Earth, we are always surrounded by air. At sea level, air pressure is strong. It pushes on everything around us. But inside a vacuum tube, this pressure is reduced. Engineers use powerful pumps to remove most of the air. The goal is to create a low-pressure environment. This is not a perfect vacuum-like space, but it is close enough. Even removing 90 to 99% of air makes a huge difference. Now imagine a train moving inside this tube. There is very little air to push against. So there is almost no air resistance. This allows the train to move much faster, and it uses less energy to maintain that speed. This is the key idea behind vacuum train systems. One well-known concept is the Hyperloop. It uses sealed tubes that stretch for hundreds of kilometers. Inside these tubes, passenger pods travel at very high speeds. These pods use magnetic levitation to float, and they use electric propulsion to move forward. Now let us talk about energy. In normal trains, a lot of energy is wasted. Friction and air resistance consume most of it. But in a vacuum system, energy is used more efficiently. Once the pod reaches high speed, it can continue with very little power. This is because there is very little resistance slowing it down. Some studies suggest that vacuum trains could use up to 50% less energy than airplanes for the same distance. This makes them more sustainable. It also reduces fuel costs and pollution. Now consider travel time. At speeds of 1,000 kilometers per hour, distances shrink. Cities that are far apart suddenly feel close. A journey from one major city to another could take less than 1 hour. This could change how people live and work. People could travel long distances daily. Jobs, education, and opportunities become more accessible. But building such a system is very complex. The tubes must be perfectly sealed. Even a small leak can let air in. This would increase resistance and reduce speed. Maintaining low pressure over long distances is a big challenge. Temperature changes can also affect the structure. Materials expand and contract with heat. This must be carefully managed. Safety is another major concern. Passengers must be protected at all times. Emergency systems must be in place. In case of failure, the system must respond quickly. Engineers design multiple backup systems for this purpose. They also test materials and designs under extreme conditions. Despite these challenges, progress is being made. Prototype systems are being tested in different countries. Companies are investing billions into research. They believe this technology can transform transportation. It is not just about speed. It is about efficiency, sustainability, and innovation. A world with vacuum trains could reduce traffic and pollution. It could connect cities like never before. The idea of removing air may sound strange, but it solves one of the biggest problems in physics, and it opens the door to a new era of travel. The future is being built inside these tubes.
This section focuses on the concept of vacuum environments and their role in reducing air resistance. It explains how low-pressure systems allow motion with minimal opposition. The key idea is that controlling the environment is as important as improving the machine. By combining vacuum conditions with the levitation, engineers can dramatically increase speed while improving efficiency and reducing energy loss.
Clapperboard Part 5: The Power of Superconducting Magnets. Now let us explore the heart of this technology. Magnets. Not ordinary magnets, but superconducting magnets. These are the key to making maglev trains possible. First, let us understand a simple idea. Electricity flowing through a wire creates a magnetic field. The stronger the current, the stronger the magnetic field. But in normal materials, electricity faces resistance. Some energy is lost as heat. This limits how powerful the system can be. Now imagine a material with zero resistance. Electricity can flow forever without losing energy. This is called superconductivity. Superconductors work only at very low temperatures. They must be cooled using special systems. Often, liquid nitrogen or liquid helium is used. This cooling brings the temperature far below zero. At these temperatures, the material changes behavior. It allows electricity to move without any loss. This creates very strong magnetic fields. These fields are powerful enough to lift heavy objects, even a full-size train. In maglev systems, superconducting magnets are placed inside the train. When activated, they interact with coils on the track. This creates forces that lift and guide the train. The train floats above the track. It does not touch it at all. This removes mechanical friction completely. Now let us look at some numbers. A maglev train can float about 10 centimeters above the track. This small gap is enough to eliminate contact. Japan's superconducting maglev system has reached speeds of over 600 kilometers per hour. That is one of the fastest land speeds ever recorded for trains. And this is only the beginning. Superconducting magnets are not only used for lifting. They are also used for propulsion. By changing the magnetic field along the track, the train is pushed forward. This is called linear motor propulsion. Instead of wheels turning, magnetic forces move the train. This makes acceleration smooth and powerful. Passengers feel less vibration. The ride is quiet and comfortable. Another advantage is efficiency. Since there is no resistance in superconductors, energy loss is very low. This improves overall system performance. However, there are challenges. Cooling superconductors requires energy. Special equipment is needed to maintain low temperatures. This adds complexity and cost. Also, the materials used are expensive. Building and maintaining such systems is not easy. But scientists are working on new types of superconductors. Some newer materials can work at higher temperatures. This could reduce cooling costs in the future. If this happens, the technology will become more practical. More countries may adopt it. Superconducting magnets are already used in other fields. For example, they are used in MRI machines in hospitals. They are also used in scientific research. This shows that the technology is reliable. Now imagine combining this with vacuum tubes. No friction, almost no air resistance, and powerful magnetic propulsion. This creates a system with incredible potential. Speeds can increase dramatically. Energy use can decrease. Travel can become faster, cleaner, and more efficient. The power of superconducting magnets is changing transportation. It is turning science into reality. And it is bringing us closer to a future where distance is no longer a barrier.
This part explores superconducting magnets as the core technology enabling levitation and propulsion. It explains how zero electrical resistance allows powerful magnetic fields. The concept emphasizes that breakthroughs in material science can transform engineering possibilities. It connects physics with the real-world applications, showing how controlling electricity and magnetism enables frictionless movement and highly efficient transportation systems.
Clapperboard Part 6. Reaching near supersonic speeds. Now imagine a train moving faster than anything you have ever experienced on land. Faster than cars. Faster than airplanes during takeoff. This is the promise of vacuum maglev systems. When friction is removed and air resistance is reduced, speed increases dramatically. Engineers believe these systems can reach speeds of 1,000 km per hour or more. That is close to the speed of sound. The speed of sound at sea level is about 1,235 km per hour. Reaching such speeds on land was once impossible. But now, it is becoming realistic. Let us understand why this is possible. In traditional trains, energy is constantly lost. Friction and air resistance slow the train down. Engines must keep working hard to maintain speed. But in a vacuum maglev system, resistance is very low. Once the train reaches high speed, it can keep moving with minimal energy. This is similar to how objects move in space. With no air and no friction, motion continues easily. Now think about acceleration. Maglev trains can accelerate smoothly and quickly. There are no gears or mechanical parts limiting motion. Magnetic forces provide steady and powerful push. This allows the train to reach high speeds in a shorter distance. For example, some designs suggest reaching 500 km per hour in just a few minutes. This is much faster than traditional trains. Now let us look at travel time. At 1,000 km per hour, distance becomes less important. A journey of 500 km could take only 30 minutes. A trip of 1,000 km could take about 1 hour. This changes how we think about travel. Cities that were far apart become connected. Daily long-distance travel becomes possible. Now consider energy efficiency. Airplanes consume large amounts of fuel. They must overcome gravity and air resistance. Vacuum trains stay on the ground. They use electric power, which can come from renewable sources. Some studies suggest that energy use per passenger could be lower than airplanes and even some high-speed trains. This makes the system more sustainable. It reduces pollution and environmental impact. But there are still limits. As speed approaches the speed of sound, new challenges appear. Even small amounts of air can create pressure waves. These waves can affect stability and comfort. Engineers must design systems to manage this. The structure of the tube must also handle high speeds. Even small vibrations can become dangerous. Precision engineering is required. Everything must be perfectly aligned. Safety systems must be extremely reliable. At such high speeds, even a small error can have serious consequences. That is why testing is very important. Engineers run simulations and build prototypes. They study how materials behave under extreme conditions. They also design emergency systems. Despite these challenges, progress is steady. Each test brings new knowledge. Each improvement brings the technology closer to reality. Reaching near supersonic speeds on land is no longer just a dream. It is a goal supported by science and engineering. The idea of traveling across countries in less than an hour is becoming possible. This is not just faster transportation. It is a transformation of how we move, connect, and live. The future is moving at incredible speed.
This section explains how removing resistance allows near supersonic speeds on land. It connects physics principles with real performance outcomes like acceleration and travel time. The key idea is that efficiency leads directly to speed. It also introduces new challenges that appear at extreme speeds, showing that innovation always brings new limits that must be carefully managed and engineered.
Clapperboard Part 7: Energy Efficiency and Sustainability. Now let us talk about something very important: energy. Every form of transportation needs energy. Cars use fuel. Airplanes burn huge amounts of jet fuel. Trains use electricity or diesel. But most of this energy is not used efficiently. A large part is wasted. Friction and air resistance are the main reasons. In traditional systems, energy is constantly lost. Engines must keep working to overcome these forces. This increases fuel consumption. It also increases pollution. Now imagine a system where these losses are reduced. This is what maglev vacuum trains offer. By removing contact, friction is almost eliminated. By reducing air, resistance becomes very low. This means more energy is used for motion, not wasted. Now let us look at some numbers. Airplanes are one of the fastest ways to travel, but they consume a lot of energy per passenger. High-speed trains are more efficient, but still face resistance. Vacuum maglev systems could use significantly less energy per passenger per kilometer. Some estimates suggest up to 50% less energy than airplanes. This is a major improvement. Now think about electricity. These systems run on electric power. Electricity can be generated from renewable sources. Solar, wind, and hydropower can all be used. This reduces dependence on fossil fuels. It also lowers carbon emissions. This is important for the environment. Climate change is a global challenge. Transportation is one of the largest sources of emissions. Reducing emissions can help protect the planet. Vacuum maglev trains could play a key role in this. Now consider maintenance. Traditional trains experience wear and tear. Wheels, tracks, and mechanical parts degrade over time. This requires regular maintenance. Maintenance consumes resources and energy. Maglev systems have fewer moving parts. There is no contact between train and track. This reduces wear. This also reduces maintenance costs. Over time, this makes the system more efficient. Now think about noise pollution. High-speed trains and airplanes create a lot of noise. This affects people living nearby. Maglev systems are quieter. Without contact, there is less vibration and noise. Inside vacuum tubes, sound is also reduced. This creates a more comfortable experience. Now let us talk about long-term impact. Efficient transportation can change economies. Faster travel increases productivity. Reduced energy use lowers costs. Cleaner systems improve public health. All of this supports sustainable development. However, building these systems requires investment. The initial cost is high. Infrastructure must be carefully planned and constructed. But over time, the benefits can outweigh the cost. Lower energy use, reduced maintenance, and faster travel create long-term value. Governments and companies are studying these benefits. They are analyzing data and running models. Many believe this technology is worth the investment. The goal is not just speed. It is smarter use of energy. It is reducing waste. It is building systems that last. Vacuum maglev trains represent a shift in thinking. From power and consumption to efficiency and sustainability. This is the future of transportation. A future where speed and responsibility go together. And where innovation helps protect the world we live in.
This part focuses on energy efficiency and sustainability. It explains how reducing resistance leads to lower energy consumption and environmental impact. The concept highlights a shift from power-heavy systems to smarter, cleaner solutions. It connects transportation with global challenges like climate change, showing how innovation can improve both performance and responsibility toward the environment.
Clapperboard Part 8, Engineering Challenges and Safety. Now let us look at the difficult side of this technology. Building vacuum maglev systems is not easy. It requires advanced engineering, precise design, and careful planning. Many challenges must be solved before this system becomes common. The first challenge is the vacuum tube itself. The tube must be strong and completely sealed. Even a small leak can let air enter. This increases air resistance and reduces efficiency. To prevent this, engineers use high-quality materials. They design tubes to handle pressure differences. Outside the tube, air pressure is normal. Inside, pressure is very low. This creates stress on the structure. The tube must be strong enough to handle this at all times. Now think about length. These tubes can stretch for hundreds of kilometers. Keeping such a long structure perfectly sealed is very difficult. Engineers use special joints and seals. They also install sensors to detect leaks quickly. If a leak happens, systems can respond immediately. The next challenge is temperature. Weather changes can affect the tube. Heat can cause materials to expand. Cold can cause them to contract. This movement must be managed carefully. Otherwise, it can damage the structure. Engineers design flexible systems to handle these changes. Now let us talk about safety. Safety is the most important part of any transportation system. At very high speeds, safety becomes even more critical. Passengers must be protected at all times. Multiple safety systems are built into the design. For example, there are emergency braking systems. Even without friction, magnetic systems can slow the train down. There are also backup power systems. If the main power fails, backups can take over. This ensures that the train remains stable. Now consider emergencies. What happens if there is a problem inside the tube? Engineers design escape systems. There are emergency exits at regular intervals. There are also communication systems to guide passengers. Air pressure can be adjusted if needed. This helps keep passengers safe. Another challenge is alignment. At high speeds, even a small misalignment can cause problems. Tracks and tubes must be perfectly straight and smooth. Advanced sensors constantly monitor the system. They detect any small changes and correct them. Precision is extremely important. Now let us consider power systems. Maintaining a vacuum requires continuous energy. Pumps must keep removing air. Cooling systems must maintain superconductors. All of this requires reliable power. Engineers design systems with redundancy. This means there are multiple backups. If one system fails, another takes over. Now think about cost. Building this infrastructure is expensive. Materials, technology, and land all add to the cost. But engineers believe that long-term benefits can justify the investment. Testing is another important step. Before full systems are built, prototypes are tested. These tests help identify problems. They also improve design and safety. Each test brings new data. This data helps engineers make better decisions. Despite all these challenges, progress is steady. Technology is improving every year. New materials and methods are being developed. Safety systems are becoming more advanced. The goal is to make the system reliable and secure. Engineering challenges are part of every new invention. They may seem difficult, but they can be solved. With time, research, and innovation, solutions are found. Vacuum maglev systems are no different. They represent a bold step forward. A step that requires effort, but offers great reward. The future depends on solving these challenges.
This section examines engineering challenges and safety requirements. It explains that advanced systems demand precision, strong materials, and reliable backup systems. The concept emphasizes that innovation is not only about ideas but also about execution and safety. It shows how solving practical problems is essential to turning futuristic concepts into reliable, real-world transportation systems.
Clapperboard Part 9: Real-World Projects and Progress. Now let us look at what is happening in the real world. Vacuum maglev technology is not just an idea. Many countries and companies are already working on it. They are building prototypes, running tests, and improving designs. One of the most well-known ideas is the Hyperloop. This concept was introduced in 2013. It proposed using low-pressure tubes and high-speed pods. Since then, several companies have started developing this system. They have built test tracks and small-scale models. Some tests have already shown promising results. Pods have reached speeds of over 400 kilometers per hour in test environments. This is still lower than the final goal, but it shows progress. Now let us look at maglev trains. These are already in use today. China operates a maglev train in Shanghai. This train can reach speeds of around 430 kilometers per hour. It connects the airport to the city quickly and efficiently. Japan is also leading in this technology. They have developed a superconducting maglev system. In 2015, their test train reached a speed of 603 kilometers per hour. This set a world record for train speed. Japan is now building a new maglev line. It will connect major cities with very high speed. This shows that the technology is practical. Now combine this with vacuum systems. Some countries are testing low-pressure tube designs. These are early-stage experiments. Engineers are studying how to maintain vacuum conditions. They are also testing safety systems and materials. The goal is to move from small tests to large-scale systems. Governments are also involved. They are funding research and supporting projects. They see this as a future transportation solution. Private companies are investing billions of dollars. They believe this technology can change travel. Now consider the timeline. These systems are still under development. It may take several years before full-scale networks are built. Infrastructure takes time. Testing and safety approvals are also important. But progress is steady. Each year brings new improvements. Now think about global impact. If successful, this technology could connect cities and countries. Travel between distant locations could become much faster. This could improve trade, tourism, and communication. It could also reduce pressure on airports and highways. Now consider competition. Different companies are developing different designs. Some focus on speed. Others focus on cost and efficiency. This competition drives innovation. It helps improve technology faster. Now let us talk about public acceptance. People must trust the system. They must feel safe using it. Education and testing help build this trust. As more successful tests happen, confidence will grow. Now imagine the future. You wake up in one city. You travel hundreds of kilometers in less than an hour. You arrive quickly, safely, and comfortably. This is what these projects aim to achieve. From early ideas to real systems, progress is happening. Step by step, the future is becoming real. Vacuum maglev trains are moving from concept to reality, and the world is watching closely.
This part highlights real-world progress and ongoing projects. It shows that the technology is moving from theory to application through testing and environment. This concept focuses on gradual development, competition, and collaboration. It explains how innovation evolves step by step, building confidence and proving that even the most advanced ideas can become practical solutions over time.
Clapperboard Part 10, The Future of Transportation. Now let us look ahead. What does the future of transportation look like? For hundreds of years, humans have tried to move faster. From horses to steam engines. From cars to airplanes. Each step reduced travel time. Each step changed how we live. Now we are on the edge of another major shift. Vacuum maglev trains could redefine transportation. They combine multiple breakthroughs into one system. No mechanical friction. Almost no air resistance. High-speed magnetic propulsion. Together, these create a new level of efficiency. Now imagine a world connected by these systems. Cities hundreds of kilometers apart feel close. Travel becomes fast, smooth, and predictable. Delays caused by traffic or weather become less common. Daily life begins to change. People can live farther from their workplaces. Housing pressure in big cities may reduce. Smaller cities can grow and develop. Economic opportunities spread across regions. Now think about global impact. Countries could build networks connecting major cities. International travel may also change. Future systems could connect neighboring countries. This could improve trade and cooperation. Now consider environmental impact. Reduced energy use means lower emissions. Electric systems powered by renewable energy can reduce pollution. This supports global efforts to fight climate change. Transportation becomes cleaner and more sustainable. Now let us talk about innovation. New materials, better superconductors, and smarter systems will improve performance. Artificial intelligence may help manage operations. Sensors will monitor every part of the system in real time. This will increase safety and efficiency. Now consider accessibility. As technology improves, costs may decrease. More countries may adopt these systems. Over time, they could become common. Just like airplanes once seemed rare, but are now widely used. Now think about challenges. Large investments are still required. Infrastructure must be built carefully. Safety must always come first. Regulations and standards must be developed. But these challenges are not new. Every major technology faced similar obstacles. With time, they were solved. Now imagine a simple journey in the future. You enter a station. You board a pod. There is no noise, no vibration. The pod begins to move. Within minutes, it reaches incredible speed. You travel hundreds of kilometers quickly and comfortably. Soon, you arrive at your destination. The journey feels effortless. This is not science fiction. It is a possible future based on real science. Researchers, engineers, and governments are working to make it real. The transition from wheels to levitation is a major step. The move from air to vacuum is another. Together, they push the limits of what is possible. Transportation is not just about moving people. It is about connecting lives, ideas, and opportunities. Vacuum maglev trains represent more than speed. They represent progress. They represent innovation. They represent the future. And that future is closer than we think.
The final section explores the long-term future and impact of the technology. It connects transportation with social, economic, and environmental change. The concept emphasizes that faster travel reshapes how people live and interact. It presents innovation as a force that reduces distance and expands opportunity, showing that technological progress ultimately transforms society in meaningful and lasting ways.